Welcome back, everybody. Once again, I'm Dr. James Ovsenka, University of New England, professor of physics, here to give you the last installment on the free particle. We're going to examine a really important biological application, which is buoyancy. We're going to go through those details so that it can help you with the long-form buoyancy lab. And we're going to do one last attempt to review action-action pairs. So let's begin. It's really kind of cool. Buoyancy is an amazing feat of evolution. Aquatic animals can adjust their bodies to compensate for depth. Bony fish, for example, have something called swim bladder, which they can adjust the size of it in order to make themselves positive, negative, or neutrally buoyant. And that's in fact the focus of the laboratory that we're going to be looking at is the volume of the object. And how buoyancy changes with it. Other types of critters like sharks have oil-filled livers which they can adjust, and there's a variety of techniques such as dynamic lift, which just simply means you're going through the water and you can use your fins to move yourself up and down through the water column. Other types of critters just simply have lots of fat, which is naturally buoyant, or gas in order to adjust themselves. And my favorite is the marine animals like the sperm whale, which has an amazing evolutionary ability to dive down to depths of 2 kilometers, which is 200 atmospheres. That's insanely huge. How the heck does it do that if it's got this big old hunkin' lung in there that has so much air fit inside? Well, it turns out that they can squeeze down that lung and its rib cage to a very small size as they go down in depth, so they don't have to worry about bursting anything. And then the next question is how do they stay down there so long? Well, as this research article points out, they have the ability to store oxygen, and much more oxygen than humans can, in both their blood and in their muscle, which allows them to go ahead and hunt as they go down there, and then use dynamic lift to get themselves back up to the surface. Other types of critters just try to say it's about the same density as the seawater, and it works really well. So anyways, this is really cool stuff. We're going to go on to the next page here and look at the buoyancy principles. Let's imagine immersing a can of high fructose corn syrup soda in a bucket of water. Corn syrup has a density much greater than water, so if you take a can of sugary soda and drop it into a bucket, it'll sink. On the other hand, it's really quite interesting. If you go ahead and get a diet soda, it'll often float because the density of the materials inside is less than water. We're going to go ahead and interaction force diagram the soda can and then solve for the buoyant force. So we've got the string interacting with the soda can, you got water pushing on the soda can, and you got the earth. And the earth is the largest force. It's pulling it down, and as long as the density of the soda can is greater than water, and the buoyant force is up and the tension is going to be up on the string. Whether or not the buoyant force is larger or smaller, the tension completely depends upon the density of the object that you're submerging. Ultimately, we can use that force diagram to make an equation to solve for the buoyancy. So this is an experimental result that we can get, and to some extent that's what we're doing, and we'll be doing that directly by actually measuring the tension directly on the string and zeroing out before we start the weight of the any attached additional materials before we submerge it into the water. Okay, so you measure directly with the iLab the tension, and as you submerge the object, and thereafter you've tared it, and you'll be measuring the buoyant force, which is quite cool. That is just an empirical result. On the other hand, how do we predict the buoyant force of an object? And the answer is what Archimedes figured out. He posited the buoyant force is equal to the weight of the displaced water. This is a really amazing result. Okay, there's a stamp there from Greece that was made in his honor. Since mass is related to density through density times the volume of the object, we can find the weight of the displaced water. Okay, that's density of water times gravitational field times the volume submerged. And that, of course, is going to be the buoyant force. Okay, now your job in the lab is to get the experimental result of the buoyant force with the iLab and the displacement using your graduated beaker and plotting those two and extracting the slope. And the slope is the key thing here, and it's a little bit more challenging than anything we've done previously because it's a complex slope. It consists of more than one constant. Okay. All right. So now we're going to do one last review here of the action-action pairs. So this is a thought activity. It's found in the workbook. I'm going to encourage you to go to that page. It's the very first activity that's in the conceptual C problems. It involves three different scenarios. One, which is both objects are standing still. Velocity equals 0. Second one is this monster mosquito lifting up a car and they're moving at a constant speed. And the third one is baseball on top of a piece of paper falling faster and faster. Your job is to draw interaction diagram between each object, 1 and 2, for every scenario here. And then from that, draw the forces only between the objects, no other forces. We don't care about the earth pulling it down, the ground pushing it up, or any air, whatever else is involved. What are just the forces between the two objects? And then rank them. Is the force of 2 on 1 greater than, equal to, or less than the force of 1 on 2 in each of these scenarios? And I really encourage you to sit down and do it. Okay, we've gone through this many, many times. The answer is in your interaction diagram. All right, I'm going to give you a 10-second delay here to pause the video and try it out, and then we'll come back and finish this off. So I'll just wait patiently right now. So have you tried it? Really, it's worthwhile. Okay, one last chance here. Go ahead and pause it. Check it out. If you're impatient, we'll just go on to the next page right now. So here's the answers. So each of these are the interaction diagrams just between the two objects. And one of the things you'll notice when we go to the force diagrams, all those forces are equal and opposite. The exact same size, regardless of how big one is compared to the other. Okay? That is what an action-action pair means. Okay? Regardless of mass, these forces are always equal and opposite, and regardless of the kind of motion, standing still, constant speed, or changing speed, it makes no difference. All right, so here's our last review. Interactions between two objects are always equal and opposite. Okay, these are the action-action pairs. Equal and opposite forces exist between two objects regardless of the motion of the objects. Okay, whether or not they're standing still, moving at a constant speed, or accelerating. When the forces on an object are in equilibrium, this is only constant velocity, then the total forces add up to 0, and this is what we'll be using in the buoyancy lab also, as well as the last two labs we did. And the buoyancy force lab is our first lab in which the slope is composed of more than one constant. Very good. Okay, so we're going to be moving on shortly to our next really important physics concept, which is elasticity. And so important that we separate it out because it'll also help us introduce the idea of energy. So in any event, it's good to see y'all, and we'll be back with another installment shortly.